Hi everyone, welcome to the third video for week 2 on multiplication and addition rules. These rules are going to help us find probability for compound events that are made up of more than one possible outcome. Let's start with the multiplication rule. The multiplication rule is used for probabilities with the keyword AND, A and B. And we can see that region in purple here in this picture. A and B is the overlap, the part of the graph that A and B have in common. It is important that A and B are part of the same sample space, meaning we're drawing from the same population, same deck of cards, same pair of dice. If we are finding P, A, and B, it is equal to the probability of A times the probability of B given A. The important thing being the keyword AND usually means to multiply when we're doing probability problems. AND means multiply. We can take this and rewrite this. We can solve it for that conditional probability, and we end up with that formula we saw in our first video. The conditional probability is A and B divided by the probability of A, which was the given statement. So that probability definition for conditional probability just came from the multiplication rule. Another nice thing is if we know A and B are independent, meaning the probability of B happening doesn't depend on A, that conditional probability just becomes the probability of B. So PA and B would just be PA times PB. The addition rule is used for OR situations, probabilities with the keyword OR, A or B. And you can see that marked in this graph, and that's everything that's been shaded in. In general, in probability problems, when you see the keyword OR, it's telling you to add. Just like last time, we are limited. A and B must be part of the same sample space to use this rule. But you're not going to see any situations in this class where I'm giving you things from different sample spaces. So if we are using the keyword OR, PA or B is equal to PA plus PB minus PA and B. The reason we have to subtract is that PA and B gets counted twice. It gets counted in PA, that whole red circle. It then gets counted again with PB, that whole blue circle. So that purple chunk got counted twice. So we're subtracting off the double count. We don't want to double count A and B. If those events are mutually exclusive, meaning in this picture those two circles don't overlap, this just becomes PA or B is PA plus PB. The important thing is to remember anytime you're doing the addition rule, subtract off anything that got double counted. Okay, we're going to spend the rest of this video doing examples so you can get practice figuring out how this works. So we're going to start with example 315. It says Carlos plays college soccer. He makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in a row in the next game. A equals the event Carlos is successful on his first attempt. PA equals 0.65. B equals the event Carlos is successful on his second attempt. PB equals 0.65. Carlos tends to shoot in streaks. The probability that he makes the second goal, given that he made the first goal, is 0.9. So let's go back, sorry. A says, what is the probability that he makes both goals? So we know 3 things. PA is 0.6, PB is 0.665, and PB given PA is 0.9. and we want to know probability he makes both goals. Both goals is A and B, first goal and second goal. I know that and, or both, mean multiplication rule. So PA and B is equal to PA times PB given A. So in this case, it's the probability that he makes that first shot times the probability he makes the second shot given that he made the first. Because we know he shoots in streaks, he's more likely to make that second goal if he made his first. So PA and B is 0.585. Okay, so we're going to add that down to the bottom. We now know A and B is 0.585. And let's take a look at that second part. B says, what is the probability that Carlos makes either the first or the second? So makes first or second, that's A or B. And we know or means add. And our addition rule is A or B is PA plus PB. Oh my goodness, Andrew, minus, poor Andrew's having an issue today, minus PA and B. So we know that individually, the probability that he makes a shot is 0.65. So 0.65 plus 0.65, and then minus that double count that he makes both A and B, which we found in the last part, 0.585. So 0.65 plus 0.65 minus 0.585 is 0.715. The probability that he makes the first or the second is 0.715. Notice that if you forgot to subtract the overlap, 0.65 plus 0.65 is going to be bigger than 1. And we know that individual probabilities, or any probabilities, can't be bigger than 1. We don't expect that he's going to make A or B 130% of the time. That's nonsense. So when you're doing that addition rule, there is kind of a check. Oftentimes when you add just the first two and you forget to subtract that overlap, you'll end up with a probability that's not possible. And that's that indicator to you. You need to go back and check, did you subtract the overlap or not? Okay, next one. Part C says, are A and B independent? So we had 3 checks for independent. The easiest check is A and B equal to PA times PB? The other checks are the given probabilities equal to the individual probabilities. But I'm going to check that A and B, is it equal to PA times PB? Well, PA and B is 0.585, and PA times PB, 0.65 times 0.65, is 0.423. So no, these are not independent events. We can also see that a little bit more directly. PB is 0.65. PB, given that A has happened, is 0.9. So we know that what happens second depends on what happens first. So A and B are dependent. The last question is, are A and B mutually exclusive? And mutually exclusive is asking about that overlap. Do A and B have anything in common? To check that, we look at A and B, and the probability of A and B should be 0. Well, we calculated A and B to be 0.585, so we can see that these are not mutually exclusive events. So let's try another one. So example 3.17, Felicity attends Modesto Junior College in Modesto, California. The probability that Felicity enrolls in a math class is 0.2, and the probability that she enrolls in a speech class is 0.65. The probability that she enrolls in math, given that she enrolls in a speech class, is 0.25. So we're going to let M equal math class, S equal speech class, and M given S is math given speech. And we've got 4 questions. So what is the probability that Felicity enrolls in both math and speech? What is the probability she enrolls in math or speech? And then we check independent, mutually exclusive. So our first question is, what is the probability that Felicity enrolls in math and speech? Let's pull up what we know about this system from the problem. We know probability she enrolls in math is 0.2, probability she enrolls in speech is 0.65, and the probability that she enrolls in math and speech is 0.25. And we're asked math and speech. And we know the key word "and" means multiplication rule. Now I'm going to use a cool trick here. I know that M and S should be equal to S and M because the "and" keyword is looking for the overlap, and the order that I list them in doesn't matter. It's that same chunk of overlap in a graph. I'm writing it this way because we already know how to find this one. We know that S and M is PS times PM given S, and we have PM given S. So for those "and" probabilities, you can always flip-flop the order. You cannot flip-flop the order for conditional probabilities. So if you need to make an adjustment based on what you have, start at the beginning and flip those variables for the "and" statement around. And this is nice. We have both of those. PS is 0.65 and PM given S is 0.25. So the probability that she enrolls in both speech and math, or math and speech, is 0.1625, or 16.25%. So keep that in mind. We're going to go ahead and tackle the next one. It says, what is the probability that Felicity enrolls in math or speech? We know OR is the addition rule. So M or S is PM plus PS minus that double count of PM and S, which, fortunate for us, we just found that. We know PM and S is 0.1625. So PM or S is 0.2 plus 0.65 minus that double count we found in the last problem, or 0.6875. So the next 2 problems are checks for independence and mutually exclusiveness. So are M and S independent? So check for independence. The given probability, math given speech, should equal the probability that she takes math by itself, and it's not. The given probability, M given S, is 0.25. PM by itself is 0.2. So we know that Felicity is more likely to take math if she's already taking speech. So M and S are not independent. They depend on each other. For mutually exclusive, we're looking for overlap. So to check for this, we look at that "and" probability. M and S should be equal to 0 if there's no overlap, if M and S have nothing in common. From part A, we know M and S is 0.1625, which is not 0. So M and S are not mutually exclusive. Okay, so what I'd like you to do is do this, try it on your own. Pause the video, take a few minutes. Remember to check those keywords and "or" and the rules for given probabilities. And then I'm going to go over the solutions. So for PB prime, we're looking for the probability of the complement of B, which we know is 1 minus PB, or 0.6. D and B, we use the multiplication rule, PB times PD given B, which ends up to be 0.2. The probability of B given D is B and D divided by PD, which is 0.6667. And you'll notice that's different than PD given B. So the order in those conditional probabilities matters. Next one's a little tricky. It asks for the probability of D and the complement of B. So this would be the probability of D times the probability of not B, given that D's already happened. And I happen to know for conditional probabilities, I can use that complement rule as long as it's that first event I'm looking at. So PD times 1 minus the probability of B given D is 0.09999. It's important to note that it doesn't work if it's the complement in the second half of that statement. PB given D and PB given not D are not complements. So it only works if it's the complement of the first event, not the given event. Last one, we know for D given not B, it should be the probability of D and not B divided by the probability of not B. And from part A and D, we have both of those, and dividing we get 0.1667. Before you go into panic, I'm probably not going to be mean. Matter of fact, I'm confident I'm not going to be mean. I'm not going to ask you questions like D and E on your test. But if you see them, you now have a little bit of a hint on how to tackle them. I do expect you to be very comfortable with A through C by the end of this week. Those are very common probability situations that you should know how to calculate. All right, if you have any questions, please contact me. Otherwise, I'll see you in the next video.